Cool. So proposition 14. So we're going to do oh, I'm on blue. I'm going to do proposition 14. Okay, so this one, I'm going to draw the picture first, right? So I've got a line AB like this, and I've got a line CD, right, with B lying on. Well, actually, let's stop for that. CD here, right? So if AB is a line, well, actually, I should have said let AB be a line. Let AB be a line. If the angle ABC and the angle ABD sum to two right angles, then CB, when extended, passes through D. So maybe I should have not jumped the gun there. So the picture there is you got AB as a line, right, and CB is a line segment. BD is a line segment. I've drawn it straight, but we're not assuming that it's straight. And I guess the content is that if the two angles ABD, I'll mark it here, ABC and ABD, right? ABC is here, ABC is there, right? If the two marked angles sum to two right angles, so 180 degrees in modern language, then CB, when extended, passes through D, right? So what we're actually going to do is we're going to construct, I've drawn this thing in a bad way. You want to construct a line here. A line here. Actually, let me just erase the marked angles to make it not super confusing, right? So the construction there is that we're going to extend the line CB to CE. So we're gonna kind of extend it out there like this. I'll put it E there, right? And we're gonna claim that we're gonna start with this, right? So we're gonna extend CB to a line CE. So that's the yellow line right there. Then by proposition 13, the sum of the two angles ABC and the angle of this new line ABE is equal to two right angles, to the sum of two right angles. I'm guessing back then they didn't have the notion of like degrees or anything. They just have to say the sum of two right angles, which feels a bit clunky to say now, but I guess in the text that's kind of how it's presented. So I'll keep with the terminology. So basically it's saying that if you extend this line, then you add the two angles that are adjacent. Well, of course, it adds 180 degrees or two right angles, right? So now we're going to subtract ABC from this sum, right? And since angle ABC, well, hang on, give me 1 sec. Let me just write what it is. We're going to subtract ABC from this sum, and the sum is ABC plus ABE, right? And we're also going to subtract it from the sum ABC and A, B, D. Whoa, what happened there? Hang on. Wow. I was trying to scroll because I thought that was in another app. Oh, that's hilarious. So don't do that. Okay, and so this implies so these are equal, right? So I'm just going to put in brackets here that this is equal uh, to right angles by above. This is also equal to two right angles because so what we assumed. So therefore, ABE is equal to angle ABD, right? And so BE coincides with BD, right? Because it's the same angle, it's got to be the same line, they got to line up. Yeah, so it's a little bit roundabout the way they've done it, but I guess the yeah, you've got basically these two angles, right? They add up to 90 degrees, 180 degrees, right? If ABC, if CBD were not in a straight line, this can't happen, right? So then BC has to line up with BE has to line with BD, so it's really the same line. So there you go. Cool. All right. So I'm gonna pass it back over to Dan for 15.
Great. Yeah.
You're welcome to do 16 too if you want.
Okay, we'll see.
Yeah.
Proposition 15. So this says if two straight lines cut one another, as in the following diagram, I'll call these lines AB and DC and their point of intersection E. So if they cut one another, they make the vertical angles equal to one another. With many propositions in Euclid, I find I don't understand the statement until I start reading the proof, just because it's all written in words rather than making use of symbols. But
Oh yeah, totally. I didn't even try. I just went straight to the symbols.
yeah, that's right. I'm trying to be a bit old school about it. But so what he means is, so AED is equal to CEB, and also that AEC is equal to DEB. I can see how I'm not actually sure. So this comes down to see that those two statements are implied. You have to understand what vertical angles means, I guess, and I don't. But okay, so let's get on with the proof.
Did he make use of the angle AED notation though?
No. I mean, He doesn't have the angle notation. For angles, he gives the three letters, that's right. So in the proof, he actually spells out what he means, but I'm just not sure that I, strictly speaking, would interpret the content of the proposition as indicated by its proof from this sentence that is written here. Okay, so we have the picture, and here's the argument. So the straight line AE stands on the straight line CD. AE stands on CD, and by proposition 13 we know that that makes two right angles. That is, if we take AED, I'm going to write comma instead of plus, which is what Euclid does, not to deliberately disagree with Kenneth, but just because it's interesting to think about why Euclid might do that. Okay, so AED CEA which together are two right angles. And that's proposition 13. Okay, so similarly, since DE stands on the straight line AB, also AED and DEB make two right angles. For the same reason. So the argument's the same as before. So subtracting AED from both. So since equal, I guess strictly speaking, the common notion has that adding equal things to equal things yields equal things. So I don't know, strictly speaking, maybe there's an argument missing for common notion 2 is if equals be added to equals, the wholes are equal. Common notion 3 is if equals be subtracted from equals, the remainders are equal. Okay, so I didn't quite catch Euclid there. Right, so if I subtract AED from both, that is from this combination and from this combination, both of which make two right angles, and here I'm invoking, I guess it's a bit funny, I don't know why it's a postulate rather than a common notion, but all right angles are equal to one another. I guess that's kind of interesting. We know how to bisect right angles, and we know how to combine right angles, so I suppose anything that looks like, using powers of 2, we can develop a system of numbers already, and we know that any sums of any powers of 2, they're the same, according to that postulate and common notions 2 and 3, I guess. Okay, so subtracting AED from both, we have, and this is, as I said, by common notion 3, that AEC is the same as DEB, which is one of the things I wanted to prove. And the remaining proof is similar, I won't give it. So similarly, AED is equal to CEB. Okay, any questions?
You seem to have some criterion for what should be a common notion and what should be a postulate.
Don't you?
Well, I'm just curious how you separate them.
Yeah, I don't know. I don't know why the properties of equality are common notions and not postulates, and why, however, the equality of right angles is a postulate rather than a common notion. It seems like he wants to put things to do with the properties of equality in the postulates, but the postulates tend to be something like numerical, right? Some things are bigger than other things, wholes and parts, equals. There's no lines or angles in the common notion, so I guess that's why it's in the postulates, because it's kind of domain-specific in the sense that it's about geometry, whereas the common notions is kind of about equality and greater than.
Right.
So I get why it is where it is, but I feel like there's a bit of a, like from a modern point of view, the common notions is about the number system, but the notion of right angles in postulate 4 is kind of where there's this overlap between the number system and the geometry, right? One of the places, also the lengths. But yeah, I feel like we'll see when we get to the foundation of numbers and measurement within Euclid's system. But if you think about how you construct, well, maybe I'll make this comment when we get to it, but it's not that postulate 4 is unrelated to how you tell whether two numbers are the same, I think. Okay. Well, you go ahead with proposition 16, Kenneth.
Okay, no worries. So 16. So this is a slightly longer one. So hopefully I finish in time. I've got 10 minutes, so I think that looks good. 16, right. So 16 is about proving that an external angle of a triangle is greater than either of the two opposite angles. So again, I'll start with a diagram of a triangle ABC. I'll try and be compact here and not take up too much room. ABC. Right. So the statement is that we let, I guess I kind of verbally said what Euclid said informally, so I'll give the formal statement now. So let ABC be a triangle. We want to extend BC to a line BD, so I'll do that right now. Extend it to line BD. Then the external angle. So the external angle is angle ACD is greater than spelled than wrong. It's greater than, still looks wrong, angle ABC and angle BAC. No, I'm not saying that it's greater than the sum of these two. It's just individually. It's greater than ABC and maybe just to be more precise, and greater than, because I think there's a possibility of confusion there, BAC. Okay, so in the proof, what we're going to do is we're only going to prove one of these statements. The other one is analogous, and we can essentially apply the same proof on to the just to a slightly different line. Right? So the proof goes like this. The proof we show that angle ACD is greater than angle BAC. Okay, and the other one we can leave for the reader to complete. So the construction, we're going to do a few things here to augment our diagram. So construction. So I'll draw in the construction as we go. So we'll let E be the midpoint of AC, a point on AC such that, draw it in E, right, such that AE is equal to EC. And we know we can do this by proposition 1.10, or proposition 10, right? So I'll just put in brackets here, proposition 10. And I'll also mark the equal sides here, right? So the next line of construction is that we let F be a point, not on AC, all right, just a point, such that BE is equal to EF, right? So draw this in. BE is here, and EF is here, right? So we want these two line segments to be equal, and the point where this extends to is called F, right? And this is possible by another proposition that we've talked about before, and that would be proposition 3. So it's early on, right? Tells us we can extend the line out from a point of given length, right? And so we're just going to join up F and C, just for completeness of the diagram. And so you can probably already see where we're going with this. We've got two triangles there that look like they should be congruent. And so that's what we're going to show. So the claim is that the triangle AEB is the same as the triangle, let me get this right, AEB, and it's going to be CEF. Right, and so we already see the two of the lines, the line segment 2 of the side pairs that are equal by construction, right? So since AE is equal to EC and BE is equal to EF, right? This is just by construction. And we also have the vertically opposite angles, AEB is equal to angle FEC, right? This is by the proposition that Dan just proved, which is 15, right? We see that the triangles are congruent, so the claim follows. I guess proposition 1.4, proposition 4. Okay, so now I'm going to move to the next board since we have another board, right? And so now we've got the two triangles are equal, and so now we can match up the corresponding angles, right? So therefore, the ECF is equal to angle BAC, right? These are the corresponding angles of the two congruent triangles, right? But angle ACD is greater than angle ECF. So ACD, right, is the big triangle. Angle ECF is part of it, right? Right, since angle ECF is part of angle ACD is one of the common notions. Thanks, Dan. And where am I up to? And all right, and hence we've got it, right? Because ECF is BAC, right? So maybe, yeah, putting these two together, we've got ACD is greater than angle BAC, which is what we wanted to show. And so this is the end of the proof of one of the parts, right? So I'll just note here that we can prove ACD is greater than the other angle ABC by repeating the argument, the construction and the argument, proof on the line BC. I guess, well, maybe this is not the best way of saying or repeating the proof on the other side.
Yeah, we have to extend AC out to something. Yeah.
Yeah, so like the just we have to redo the whole construction starting on a BC instead of AC.
Other way around. Oh, okay. Bisecting BC. You mean. Yeah.
Yeah, bisecting. Yeah, that's right.
Yeah. Cool.
Ooh.
Thanks.
Yeah, so this is a longer one, and I felt like you had to do. You know, we use. I like Euclid actually because we have to use a lot of things that we used before with, right? And everything is laid out in such a way where you're not, well, there are these common notions and so forth, right? That we keep using, we keep making comments about, but at least the geometry stuff is following in a very nice kind of flow, right?
Yeah, I felt like Proposition 16 was the first time I felt really happy in this book. I don't know, it felt like it actually used some of the earlier stuff, and the earlier things seemed a bit kind of,
right,
you know, like homework, but this was good.
Cool.
Yeah. I guess we'll leave it there. I'll just make one comment. I mean, one of the things I find beautiful about Euclid is this relationship between angles and lengths that is starting to come out, right? We saw it already in the earlier propositions where we deduce things about equalities of sides of triangles from equalities of angles. And the way in which the number system is built on the geometry in Euclid is not the modern way you might think of constructing numbers in mathematics, but if you think about the relationship between geodesic length and infinitesimal geometry, that is dot products, and reflect on that, and the dot products are kind of an invariant that's associated to SO2 symmetry, so it's fundamentally about angles. These ideas are still baked into the foundation of how we think about length. And no doubt the people people like Riemann who set up our current theories of how we measure length in general Riemannian manifolds and so on. I'm sure they were very aware of this source of inspiration, so it's well worth pondering not just the technical details of what's going on in Euclid, but how the different notions relate, right? How angles are related to lengths and vice versa. Okay, any other comments or questions before we move on?
Cool. Thanks, Dan. I got to drop, but I might be back later.
Yeah, thanks, Kenneth. See ya.
Cheers. Bye-bye.
All right, shall we move on over for foundations?
Let's go.
Oh, I'm going to win. You guys didn't even... Oh, no.